Hey folks, we're going to continue on with discussion of electric flux. And the first thing I'm going to do is a slightly more complicated um, uh, example. So we have, from the previous discussion, we have the definition of electric flux, which is a capital Phi in Greek, capital F in Greek, electric flux equals. Now this is the algebraic version. So it's E dot A. The magnitude of this would be the magnitude of E times the magnitude of A times cosine of the angle between them. Well, that's the algebraic version. If you have a constant electric field, this is perfectly fine to use. However, what if we have a field that varies over position? So, for instance, let's say I give you the following electric field. Let's say there's an electric field that equals 2y squared in the I hat direction. And let's say I have an area that looks like this. And I guess I'll draw this over here. So we're going to have our coordinate system. All right, now this coordinate system, we're going to do the following. Okay, this is going to be x and y and z. And let's say I have an area that looks like this. Okay, it's a rectangle. And it's in the YZ plane. Okay, and I'll even throw numbers at you. Let's say this intercept right here for z is 4. And let's say the y-intercept is 2. So we're going to actually do some numbers here. But don't worry, you won't need a calculator for this one. Okay, so let's start with this electric field. Well, what on earth does this look like? Well, first of all, it points in the I hat direction. That's to the right. So whatever field I draw, the arrows better all point to the right. Okay. Now, you'll notice that the field varies with y. As you go up or down from y equals 0, you get a stronger field. So what you're going to see is near the bottom of this rectangle, there's going to be very few field lines poking through it. And those field lines will point to the right. Okay, so I'll just draw a couple representative ones. But as you go up the rectangle, as y gets bigger, you're going to get a stronger field, which means more field lines poking through that area. And near the top of the rectangle, you're going to have even more field lines poking through that area. The field gets stronger as you go up or down, but in this case, we're just going up as you increase y. So that's what our electric field lines would look like poking through that area. Now, for now, I'm just going to find the magnitude of the flux. I don't care if it's plus or minus. The amount of flux entering the left face of the rectangle is going to equal the flux leaving the right face. So I just want the magnitude of it. Well, in this case, we can't do just E dot A because E varies. It's not constant anymore. So guess what we have to do, all right? We have to integrate. And so the more general definition of electric flux, the more useful one, okay, is the following. You're going to do a double integral. Oh my gosh, a double integral of E dot dA. Okay, now, in virtually all the examples I'm going to give you, you're not actually going to do a double integral. And I'll explain. So first of all, double integral, why is it double? Well, because there's an area that's got 2 dimensions. So like for instance, if this flux or this field varied over y and z, well, then you would have to integrate twice. Okay. Now, I won't do that to you. I won't give you a field that varies over 2 different directions on your rectangle. I'll just do one. Okay. So we're only going to have to integrate one time. Now, what's dA? Well, remember, d anything is a very, very, very small chunk of the thing. So for this area, we want to make a very, very small chunk. And here's where it's very important that you select a proper dA. You want a dA through which the field is constant. Now for a rectangle, there's 2 dAs that make sense. There is dAs that run this way. I'll call that 1. And there are dAs, and there are dAs that run vertically. I'll call that 2. Which dA, which tiny sliver of that rectangle would be more appropriate in this example? 1. Because if you look at 1, the electric field, if I make that thing skinny enough, the electric field within that dA is constant. Whereas if I look at dA2 there, the field does vary over dA2. So I'm not going to use dA2. I'm going to use dA1. Okay. What is the area of dA1? Well, the width is still 4. The height of that rectangle is dy. All right. Now, mathematically, it's another way to look at it. Your dA should include the variable that's in your electric field. So that's a kind of way to tell if you're selecting the right dA. So in this case, because the field is constant along that dA, I only have to integrate one time. Okay. So we have our electric flux is going to equal the integral of E, which is 2y squared. And then the dA is 4 dy. Now, luckily, I don't have to worry about cosine theta here because the angle between the field and the area vector is 0 degrees, or the angle between the field and the area itself is 90. So, but the area vector points to the right, which is the cosine of that would be 1. It's the area vectors to the right, fields to the right, they're parallel. The last thing is we need our limits. Well, what does y vary from? For our rectangle, y varies from 0 to 2. So that's your limits that you're going to put. Okay. So you end up with 2 times 4 is 8. The integral of y squared is y cubed over 3. And we're going to evaluate that from 0 to 2. If you plug in 2, 2 cubed is 8. 8 times 8 is 64. You get 64 over 3 minus 0. And that's your answer, and you got your Newton meter squared per Coulomb. So that is your electric flux passing through that surface. Okay. I will do some more. I'll talk about some closed surfaces in the next video, and that'll lead us to Gauss's law. Hope that video was helpful, and thank you very much.